This is a pre-built version of the application. So let's go ahead and run it. And we'll have 5 peers that are trying to communicate, and 1 eavesdropper peer. And in this prototype project, we will be using a deterministic encryption scheme, which is a crypto system that is always producing the same ciphertext for a given plain text and key, even over separate execution of the encryption algorithm, and examples of deterministic encryption algorithms include RSA without encryption padding. So this is the first communicating peer, second, third, fourth, and fifth, and this is the eavesdropper peer. So it will pick up messages from all 5 communicating peers, and we'll go in a circle. So this one will pick up messages from this one, and this one from this one. And this one from this one, and this one from this one, and this one from this one. So Diffie-Hellman key exchange is not limited to 2 peers. It is possible to have any number of peers with no prior knowledge of each other to jointly establish a shared secret key over an insecure network. And P here is prime, and alpha is a primitive root modulo P. Now suppose that Alice, Bob, Carla, Dave, and Elena agree to use P equal to 467 and alpha equal to 2. And for the purpose of this prototype application, I had the first user that logs in, Alice in this case, enter the value for P and alpha. So let's suppose that Alice picks 4 as her secret key, and Bob picks 5, and Carla picks 6, and Dave 7, and Elena 8. Now all 5 peers calculated this common key. So 277 in mode 467. Now passive Eve here can see the values for P and for alpha. And she can see the values of alpha to the power of A, to the power of B, to the power of C, and alpha to the power of A, alpha to the power of A to the power of B, until alpha to the power of A to the power of B to the power of C and to the power of D. But she cannot see the values of all of alpha to the power of all 5 private keys, so A, B, C, D, E, which is the common key calculated here by Elena. So I went over what happened here in more details in the previous prototype project. So passive Eve cannot use any combination of the values that she sees. So she cannot use any combination efficiently to reproduce alpha to the power of A, B, C, D, E. And much larger values would be needed here to make this example secure. And as I mentioned, we are using here deterministic encryption, which can leak information to an eavesdropper peer who may recognize known ciphertext. So for example, let's have Alice. Actually, before having them try to communicate, let's have each one of them be able to receive messages from all other peers, from all other communicating peers. So we're entering here, and we'll do the same thing for each one. So now if we have Alice send this message to all other communicating peers. So here she mapped the characters to ASCII and obtained this ASCII message, and then encrypted the ASCII message and obtained this ciphertext and sent the encrypted message. And each one of the peers received the encrypted message and decrypted the ciphertext and mapped the ASCII to character and obtained the original message. Now if Alice sent the same message again, she will be sending the same ciphertext. And this is why deterministic encryption can leak information to an eavesdropper, as opposed to a probabilistic encryption scheme where we would not see the same ciphertext for the same message, like when using El-Gamal algorithm. So each one of the peers can send an encrypted message, and all the other peers would decrypt it using the common key and obtain the original message. And let's have those two exit. And the other three can continue the conversation. The encrypted conversation. So passive Eve here can see all the communications, both communication from Alice and then from Bob, Carla, and Dave. And let's exit. Now the source code for this prototype project will be available for download. Also a longer version will be available for watching by all channel members, and it will include step-by-step coding plus test running the coded application.